Okay, so today we'll start with the next part of the lecture that today we'll go through fins and also the lumped capacitance method. Hello, am I audible? Hello, yes, yes. So sorry for being late. Actually, I was having some network issue. So, anyways, I'll continue for 2 hours also for this session. Uh, so today we'll start with last class also we have discussed about we have started with the fins, and today also we'll continue with the fins. And another topic which the professor has taught is the lumped capacitance method. So we'll also see some problems on that. Okay, so I'll start sharing my. Okay. So first we'll go through some of the um, formulas which we'll be using in this uh, in today's class. So for fins, the temperature distribution for if it is infinite in length, if the fin is infinite in length, we can write as theta by theta b is equal to t minus t infinity divided by tb minus t infinity is equal to e to the power minus mx. So theta is the temperature gradient, and then theta b is the difference between the base temperature and the surrounding temperature, and this is equal to e to the power minus mx. So what is this m? M is just a fin parameter which can tell us how fast the heat is being conducted in the fin. This is given by hp by kac. Okay, so h is the uh, heat I mean the coefficient for the surrounding fluid, surrounding uh, air or liquid, anything. Then p is the perimeter of the fin dimensions, and then k is the conductivity of the fin, and then ac is the cross sectional area of the fins. Then uh, then qf is given by QF is the fin heat rate. That means heat transferred by the fin. So this is given by root over H P KAC into theta B. Okay, theta B is TB minus T infinity. And then we have efficiency. Efficiency is given by QF by Qmax. How much maximum how much actually it is transferring and how much maximum it can transfer. So this is given by QF divided by maximum is, or you can say this is theta B. Then we have effectiveness also. It can be denoted by epsilon F. This is given by QF, Q with fin divided by Q without fin. So this Q fin is this. Q without fin is okay. This is the formula with Q without fin. So if we cancel out this, we can get it as below will be H AC and on top will be P and K. So we can write it as root over Kp divided by HAC. So this is the effectiveness. And then we also have uh, lumped capacitance model in today's class. So for that, there is a dimensionless number known as Biot number, which is given as HL by K. So why this number is defined? It is because when can you consider a lumped model? When the object is very small and the temperature is uniform throughout the body, throughout the object, then you can consider it as lumped model. That means there is no I mean the resistance is very less from, suppose this is the object, and inside this object whatever is the temperature, then outside also there is the same. That means the resistance to conduction is very less inside the object. Towards the outside of the object, there is uniform temperature. That means the resistance to conduction is very less compared to the resistance to outside, that is convection. Okay, so another, then temperature distribution can be given as T minus T infinity divided by T naught minus T infinity is equal to exponential of rho v Cp T. So this part is the time constant, inverse of time constant, and then this is the surrounding temperature, this is the final temperature, this is the initial temperature. Okay, so this is just a brief overview of what we are going to do today, and then we can just start with the first question. So this question was already, I mean, I just started last class, but I couldn't complete. So we'll start with this question only. Consider two long slender rods of same diameter but different materials. So by the this term different materials, we can infer that the conductivity is different. The conductivity of both the rods are different. Okay. Then one end of each rod is attached to a base surface maintained at 100 degrees Celsius. So this, if this is the base surface, and there are two rods. I think I should draw it. These are the two rods. Okay, suppose one is A, another one is rod B. Then this base temperature, that means the temperature of this is 100 degrees Celsius. While the surfaces of the rods are exposed to ambient air at 220 degrees Celsius. Okay, that means T infinity is equal to 20 degrees Celsius. By traversing the length of each rod with a thermocouple, it was observed that the temperatures of the rods were equal at positions xa equal to 0.15 and xb is equal to 0.075 meter. That means while it was the temperature of both the rods were measured, it was seen that at some point at xa equal to 0.15 meter, here to here is the length is 0.15 meter. Suppose this is TA, and here to here at some point at xb equal to 0.075 meter. Okay, suppose this is TB. So what they are saying, it was observed that temperatures of the rods were equal at both the positions. So this TA is equal to TB. Okay, where x is measured from the base surface. So x is measured from this base surface. Okay, from here. So if the thermal conductivity of rod A is known to be Ka equal to 70 watt per meter Kelvin, then determine the value of Kb for. So in the starting of the question itself, they said it is different materials. Different materials means different thermal conductivity. So they have given the thermal conductivity for one rod. We need to find out the thermal conductivity of the other rod. Okay. So how do we proceed this? So we have TA is equal to TB. Okay, starting point is this. TA is equal to TB. So we can also write from here this thing. We can also write in terms of theta. Theta A is equal to theta B. Sorry, theta B. So I'm going to the next page. Okay. If I write theta A is equal to theta b. Now this theta is uh, t minus t infinity divided by tb minus t infinity is equal to, this is ta, this is tb. This b is for the rod b and this b is the bulk temperature. Okay, this is equal to e to the power minus mx. So in both the cases, in these three parts, in these two parts, this is constant because bulk temperature is constant and also the surrounding temperature is constant, so the difference is also constant. Okay, then this is constant, this is constant, then t, they have also given that ta is equal to tb, so this and these are also same, you can consider. So the whole thing is constant here. So this part of the equation, that is e to the power minus mx, this should remain constant. Okay, for both the rod. So how we can write it? E to the power minus m axa is equal to e to the power minus mb xb. Okay, so from here we can write as ma xa is equal to mb xb. ma is given by h p k ac. So this whole one is for a, this whole one is for b. But here they have already given in the question that they have the same diameter. Okay, they have the same diameter, that means the dimensions are same. So from here, what is dependent on the dimension? This is parameter and the area. But they have already mentioned that the dimensions are same. So perimeter and area, these are also, they will also remain same. And H is for the surrounding fluid. Surrounding fluid does not change with the rod, so that is also same. Only the thing changing is this Ka, Kb. Okay, only the different part is the thermal conductivity for different two different rods. So we can write it as K is below, right? So Ka to the power minus half Xa is equal to K, Kb to the power minus half into Xb. So what is given here? Ka is given, right? So you can solve the question, right? Can you just quickly tell me which one is the answer? K is given as 70 watt per meter Kelvin.
Show the question.
Yeah, yeah, sure. Solved.
C option.
Is it C? No, the answer is something else. Did you get like this? I have solved in this screen itself. This one and this one. Just check, you must have done some numerical error, calculation error. Oh, okay. We'll go to the next question. It's given that two long copper rods of diameter D equal to 10 millimeter are soldered together end to end, with solder having a melting point of 650 degrees Celsius. So there are two long copper rods. End to end means we are taking here. Then with solder having a melting point of, so there is some soldering here, okay? You do the soldering, and here the melting point of this is 650 degrees Celsius. The rods are in air at 25 degree Celsius. That means the surrounding temperature is 25 degrees Celsius with a convection coefficient of 10 watt per meter square Kelvin. What is the minimum power input needed to affect the soldering? Okay, here the first thing is we can consider this system as base fin system. So if you consider this as the base, if the soldering is the base, then these two can be considered as fins, okay? Then the base temperature is given to be 650 degrees Celsius, okay? With a convection coefficient of this, what is the minimum power input needed to affect the soldering? So what is Q here? So how will you find this out? Already hint is also given. The minimum power is twice the fin heat rate for an infinitely long fin. So in maximum of the case, actually to simplify the problem, you consider those fins as when it is given long rod, something long fins or long rod, those can be considered as infinitely long fins. Okay, so here it is given q is equal to twice the heat fin rate. Now why it is twice? Because if for one it is qf, for the other it will be double. I mean for both it will be double. So we know qf is equal to root over h p k ac into theta b. Now just find out what is what are all. Just you know what is h. H is given, k is also given here, 379 watt per meter Kelvin. Okay, then p is the perimeter of the fin. So if this is the rod, perimeter will be this. Okay, so perimeter will be given by 2 pi r, or you can simply write directly 2d also. Twice into r will be d. Then cross section, AC is the cross section area. That means this. If you cut a plane, then whatever uh, that area of the fin you get, that is the cross section area of the fin. Okay, then how do you define that? Cross section is also a circular region, so it will give, for circular part, area is given by pi d square by 4 in terms of diameter. In terms of radius it is pi r square. So you just directly input all the values and then let me know the answer. Theta is tb minus t infinity. Tb is also given, t infinity is also given. How much are you getting? How much are you getting? Direct calculation is given. You just need to substitute the values. Okay, should I tell the answer? It will be around 120.54. That means A, 120.9. You got this question right? Okay, we'll move to the next question. Aluminum fins of triangular profile are attached to a plain wall whose surface temperature is 250 degrees Celsius. The fin base thickness is 2 millimeter and its length is 6 millimeter. So again there is a plain wall and then they have given a triangular profile fins. Okay, this is the triangular profile fins. The fin base thickness is 2 millimeter. So this is given as 2 millimeter. The length is 6. That means if the triangle looks like this, here in this question, they have defined this as the L. Okay, and this as the S, thickness 2 millimeter. The system is in ambient air at a temperature of 20 degrees Celsius and the surface, so T infinity is 20 degrees Celsius. The surface convection coefficient is 40 watt per meter square Kelvin. H is equal to 40. Okay, then K is equal to 240 watt per meter Kelvin. Then the fin efficiency is also given, eta F. Okay, so okay, what is the question given here? They have asked to find out EF. The question is not complete here. So just find out what is the effectiveness. They have given the efficiency, you have to find out what is the effectiveness. Okay. And also find out what is the Q fin. So the question is not complete here. Just find out what is effectiveness and what is Q fin. Okay. So how to proceed this? Q fin per unit width. So in in this particular problem, they have considered this as a very small fin, and uh, the extension of this fin is very large. Okay, so if you consider this as width W, okay, then you need to find out what is the effectiveness. So effectiveness you can get as E epsilon F is given by QF by q fin with q without fin divided by q without fin. Okay, so how do you do this? Q fin is given by root over h pk ac into theta b, right? So just find out what is this. Qf can also be written as eta f into q max. Okay, so let me go to the next page. Eta f is already given. How much is it? 0 point. And q max is given as h is tb minus q infinity. H is how much? Then tb minus t infinity. Tb is the base temperature minus. Okay, we'll denote this as theta. Anyways, we can write also 250 minus 20 into AS. Now, what is this AS? AS is the surface area of the fin. So, what does the surface area mean actually? Here, this this area is considered to be very small compared to this area. Okay. So, how do you find out? You already have this. You can consider this as W, and you need this dimension, right? This dimension. That means if you consider the top view, then you need this dimension. So this, if you consider the triangle, the perpendicular is given as L, length. Okay, then how do you find out the hypotenuse? Hypotenuse, you can write it as HY, okay? Or simply, you can write it as Y. So Y square is equal to L square plus, if you consider this as T, they have given thickness T, so T square. So Y is given by root over L square plus, sorry, not T, it should be T by 2, right? T by 2 whole square. Okay, so this is the area of this actually. So it is present on both sides, this side also, and also the behind side also, that side. So the area should be twice of that. Okay, so This is just a rectangle. Rectangle area is given by width into this one. So W into Y. For two such rectangle, you get 2 into W into Y. Okay. So here you get 2 into W into Y is root over L, sorry, L square plus T by 2 whole square. Okay. Now you also see in the this formula Q without fin. Without fin is given by HAC. This is base. Okay. Theta B. This is ACB. That means this is the cross section at the base. If there was no fin, then you need to, if there was no fin at all, you need to see what is the base only. Okay, you only need to see what is the base. That's why when it is without fin, the formula changes to ACB. It's cross section only, but it's cross section at the base. That's why it's written as AC comma B. Okay, so now we will, now ACB is how much? ACB is at the base, it is T into W. Okay, just as shown in this figure. This is the base area. So this is T and this is W. Okay. So what do you get? Effectiveness is equal to 0.99 into H. Instead of AS, you can write, uh, okay, instead of TB minus T infinity, you can directly write theta B, because here below also there is theta B. You can directly cancel HAC comma B into theta B. So just cancel this out. H you can cancel 0.99 into AS. So AS is 2 into W into root over L square plus T by 2 whole square divided by this one, T into W. So W also you can cancel. Then it is 0.99 into 2 into root over L is given as 0.006 whole square plus 0.002 divided by 2 whole square divided by 0.002. So tell me how much you get and just let me know you have understood the problem or not.
$6.021 Something.
Yeah, yeah. So it's 6.02. So did you get the first part of this solution? I'll just repeat
Yes, yes.
repeat just once more, okay? Uh, this is the fin. Yeah, this is the fin, and the base wall is much bigger. Here I have shown it smaller, but it is much bigger. You consider it below the screen also. Then this is the fin, okay? The width of the fin. So in this question particularly, they have given the structure as like this, but it's not necessary the always the structure should be like this. Thus, it can also be like this. If this is the base, suppose there is so this thickness, this width can be small also, okay? So if it is given, then you can consider the width also, but if it is not given, you can simply neglect because this dimension is very small as compared to this dimension, okay? But in our case, so here you have to consider this surface area, this and also below. But in this question, this dimension is larger. This dimension is larger compared to the top and the below surface. That's why they have considered the surface area as this. Okay, so you need to see which one you should consider. By looking at the options also, you have to check actually which option, which values are matching, and you need to see which dimension you should consider. And if one dimension is very small compared to the other, you can just neglect the smaller one. And if it is given, you can also consider, I mean, if the values are given, then directly you should consider. That is the best way actually. You should consider surface area means from, I mean, all these areas are exposed to the fluid, outside fluid. So in actual, all the area should be considered. But here they have taken an exact assumption that this area is very small compared to the this W into Y. So they have considered this. So if we for solving this, we consider this height as the W and this as Y. Now for finding out the Y, we just see the top view of this triangle, and we can see that this is given as T, the base is given as T. So the base will be half of base will be T by 2, and the perpendicular is given as L. So you can directly find out what is the hypotenuse by Pythagoras theorem. It should be root over L square plus T by 2 whole square. So then after that, you just plug in the, you can directly use QF also, but in but you have, instead of directly finding out what is QF, you have, I mean, we have formulated it in terms of eta F and Q max, because eta F is given, efficiency is given, and Q max is, this is constant, okay? But in QF, you will get a term AC, cross sectional area, and that is not constant, okay? I mean, you need to integrate that and find out what is QF. So it's better you find out from here 0.99 into HAS TB minus T infinity. This is also known as theta B. Okay. Then this is the numerator part. The denominator part is given as Q without fin. That is, if there was no fin, then you just find out what is the Q. Then you get this. Okay. So till here was the first part of the question. The next part is heat dissipation per unit with heat dissipation from the fin, that is QF itself, but it's given per unit fin, sorry, per unit width. So just divide it by W. it was 0.99 into 2 into W into L square plus T by 2 square divided by W. So W just cancel it and then find out what is the Q. Just directly substitute the values. 0.99 into 2 into okay, there was an H also. H in the formula. So into H you do. H is 40. There is TB minus T infinity also. TB was 240, I guess. 250 minus 20. So how much are you getting?
Option
Option?
D.
Yeah, already 6.02 is given here. Yeah. So you got this 110.3?
Yes, 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 yes.
Okay. Let me see if there are more things. Okay, we'll start with this also. This is
In efficiency formula, there will be a tan hyperbolic will be taken. Then how it will be taken tan hyperbolic in problems.
10 hyperbolic. That is a case of that is I think a diabetic case, right? These are different cases.
Okay.
Huh. Okay, then next question is carbon steel shafts of 0.1 meter diameter are heat treated in a gas fired furnace whose gases are at 1200 Kelvin and provide a convection coefficient of 100 watt per meter square Kelvin. So again, carbon steel diameter is given. Again, you can consider the diameter to be very small compared to the length. 0.1 meter is the diameter. Are heat treated in a gas furnace. So this is the whole thing is inside a gas furnace. Whose gases are at 1200 Kelvin. That means the T infinite is given here. It's 1200 Kelvin. And provide a convection coefficient of 100 watt per. This is H equal to meter square Kelvin. If the shafts enter the furnace at 300 Kelvin, how long they must maintain in the furnace to achieve a centerline temperature of. So if this the initial temperature, the shafts enter at a temperature of 300 Kelvin. That is Ti is given as 300 Kelvin. How long must they remain in the furnace to achieve a centerline temperature of 800 Kelvin? The final temperature should be 800. So here they have, this is a problem of lumped capacitance method, lumped model. So here how, how first how do you consider it as a lumped model? So you have to first find out what is the Biot number, and then you can conclude whether it is lumped method or not. Directly you cannot jump, obviously. I said it beforehand, it's lumped method, but for finding out such a, the time duration and all, you can consider, you can start thinking in this way that it can be lumped model. So for finding out whether it is lumped model, you need to find out what is the Biot number at first. So it is given as HL by K. Also, you can also think in such a way that this surrounding is very very big in compared to, this object is very very small, so small that you can consider it, there is uniform temperature, the resistance inside the rod is very small. Okay, so Bi is given as HL by K. So do you know what is this H, sorry, this L? H is 100, K is given as this one, 51.2 watt per meter Kelvin. Do you know what is this L? This L is also known, this is also the characteristic length. So in this case, it is given as volume by surface area. Because um, this process is a volumetric process. The conduction which takes place is volumetric process. So you have to consider volume by surface area. This is the characteristic length. So volume is given by, what is the volume of a cylinder? Pi r square into L. This is LC, suppose. This and this L is the length of the cylinder, and surface area is, you have to consider the this surface area, not the cross section, because the heat transfer is taking place along this surface area. So it is 2 pi r into L. If you cancel this, you get as r by 2. So this is LC, the characteristic length. So it's R by 2. R is how much? 0.1 divided by 2 divided by 2, that is divided by 4. Diameter is given as 0.1 meter. So how much is this? So this is less than 0.1. If it is less than 0.1, then only you can consider it as lumped model, lumped capacitance. So what they have asked to find out, how long must they remain in the furnace to achieve a center line temperature of 800 Kelvin? So you need to find out the temperature. Sorry, time duration. So for such case, the temperature profile is given as T, sorry, T minus T infinity divided by Ti minus T infinity is equal to exponential of minus HAS by rho VCP into T. So you need to find out what is this T, time duration. Everything else is given, so just calculate. Um, Final temperature is 800, initial is 300, and outside is 1200, right? So 800 minus 1200 divided by, you can take here ln. Into HAS rho VCP into T. H is 100, 541 J. So just substitute the values and see. Now A by S, it is again same. It is A means the surface area. So anyways, we have calculate for the while calculating LC also we have done the same thing, V divided by AS, so it's the opposite. So it should become 2 by R, right? AS divided by V should become 2 by R. Or you can also write it as, sorry, 4 by D, because D is given. Anyways, you can calculate R also. So just calculate and find out how much is T. How much did you get? 'How much did you get? How many seconds?
860.06.
Yeah. So it's option C maybe. 859 is given here. So the nearest answer is this. So C is the answer. Okay. We'll go to the next question. A long circular aluminum rod is attached at one end to a heated wall and transfers heat by convection to a cold fluid. If the diameter of the rod is tripled, by how much would the rate of heat removal change? Just a minute. Okay, this is a again circular aluminum rod. Again same thing. Again cylinder they have given rod is attached at one end to a wall heat to a heated wall and transfers heat by convection to a cold fluid. To a heated wall. So this is the heated wall. It is again a case of fin. So transfers heat by convection to a cold fluid. So outside is the cold fluid. If the diameter of the rod is tripled, how much would the rate of would be the rate of heat removal change? Okay, for this, it's a case of fins only, right? So for fins, Q is given by root over H E K A S theta B. So everything else is constant here. H, H, K, and theta. Except the geometry of the fin, everything is constant because here the diameter of the rod is triple. That means only the dimension is changing and everything other properties are constant. So you can just write the other properties as C1 or whatever. You may not write, that is fine. I mean, it will, anyways, they are not going to change. So if I write only P and only perimeter and area will change because these are dimension related parameters. C1 root over perimeter is given by pi d or 2 pi r, or you can simply write pi d also. AS is, this is the cross section, sorry, cross sectional area you have to take, not the surface area, cross sectional area. Cross sectional area is pi r square, or you can write in terms of d as pi d into pi d square by 4. So pi is constant, 4 is also constant. So we can write everything, since everything is constant, we can write it as proportional to root over of pi d cube. Okay, so this d and this d square, they become d cube and there is a root over. You can write as d to the power 3 by 2. Okay, so q is proportional to d to the power 3 by 2. So if the diameter of the rod is tripled, so if I write q1 by q2 is d1 3 by 2, d2 3 by 2. How much would be, how much would the rate of heat removal change? That means you need to find this q2 in compared to q1. So we can go to next page. So the second diameter is given as triple of the first diameter. D will get cancelled out. So how much is the change coming? Can you just tell? How much is this 3 to the power 3 by 2? It is around 5.19 or 5.2 also you can say into Q1. So Q2 minus Q1 in terms of Q1, right? Into 100%. Percentage change you need to find out. So 5.2 Q1 minus Q1 divided by Q1 into 100. It will become 4.2 into 100. That is 420%. So there's 420% increase in heat transfer rate. So how much would the rate of heat removal change? So it is around 420. So just by tripling the this diameter of this rod, you can just increase the heat removal rate to around 420%. So this was a simple question. You got it right? Okay. Okay. This is okay. Batch processes are often used in chemical and pharmaceutical operations to achieve a desired chemical composition for the final product and typically involve a transient heat operation to take the product from room temperature to a desired process temperature. So here they have just given some examples of where batch processes are used in chemical industries, in pharmaceutical industries. Okay. Now, uh, to achieve that desired product, they also involve a transient heating operation to take the product from room temperature to the desired, how much temperature is desired to take to that. Okay. So consider a situation for which a chemical of density 1200 kg per meter cube and specific heat to 2200 joule per kg Kelvin occupies a volume of this 2.25 meter cube in an insulated vessel. So this insulated vessel, insulated means from this vessel you cannot, I mean it's totally no transfer of mass or energy. Okay, then inside this vessel there is a chemical. This is filled with a chemical. Rho is given, volume is given, and specific heat of the chemical is given. Okay, the chemical is heated from room temperature Ti equal to 300 Kelvin. Sorry, insulated does not mean there is no exchange. Insulated means there is a, I mean the rate of heat transfer will be reduced to some extent. Okay, the chemical is to be heated from room temperature Ti equal to 300 Kelvin. That means the initial temperature is 300 Kelvin to a process temperature of 450 Kelvin. That means the final temperature is 450 Kelvin. By passing saturated steam at TH equal to 500 Kelvin through the saturated steam, that means the outside steam. Suppose if the whole screen is the room, then the temperature of this room is 500 Kelvin. That means T infinity is 500 Kelvin. Through a coiled thin walled 20 millimeter diameter tube in the vessel. So inside the vessel there is a coil. Okay, the diameter of that coil is 20 millimeter. That means 0.02 meter. Steam condensation within the tube maintains an interior convection coefficient of Hi. So inside Hi is given as 10,000 watt per meter square Kelvin, while the highly agitated liquid in the stirred vessel maintains an outside convection coefficient of, so the outside one is 2000 watt per meter square Kelvin. If the chemical is heated from 300 to 450 in 60 minutes, so the final temperature is 450, it's already given before also, and the initial is 300 Kelvin. What is the required length? of the submerged tubing. So this length of this coil you just need to find out. So for this, so heat transferred from the coil is balanced by the, we can directly find such we can find such solution by balancing the energy. Okay, the heat transfer from the coil to the this chemical is balanced by the increasing energy of the this chemical, or else you can also find out like this: input minus output plus generation is equal to accumulation. Here again there is no input, so there is output is the convection, outside convection. H is, sorry, I lost the connection again. There is an accumulation term because there is presence of this chemical. Okay. So that is given by mcp delta t. So q, how do you define this energy? You can just write it as mcp dt by dt. If you consider is I mean transient, then you also, there is no generation term here, there is no input term here, there is an output because of the convection outside taking place. So that is h in s minus hs th minus t. Convection is taking place outside, so it should, the outside temperature should be taken. Outside temperature was how much? 500 Kelvin. So that is th or t infinity, whatever. And then uh, the t, the final temperature. Okay. So it can be given like this. So this also gives us the energy balance, that the heat generated by the heat transferred by the coil to the chemical is balanced by the increase in the energy inside the chemical. Okay. So here there are two H, right? One is inside HI, one is outside H naught. So instead of H, we can also write it as U, total heat, sorry, total coefficient, heat transfer coefficient. Now instead of M, we can write mass is, M here is mass, is rho into V, rho into V is AS into the diameter, or you can simply keep it as V also. So M is rho V Cp dt by dt, dt divided by Th minus T rho V Cp divided by UAS dt. Just integrate it. Here there will be minus. So integrate, if you integrate, how much are you getting? Here everything else is constant, you'll get only T. I mean, if you integrate dt, you'll get T. And here, at t equal to 0, T is equal to Ti. At T equal to T, T is, this is the final temperature, T is equal to T. Okay. Then you get such. Okay. Now how do you find out this U? You can find out U by, this is the overall heat transfer coefficient. So in the first, maybe in the first 2 weeks, we have learned how, I mean, the overall heat transfer can be find out by 1 by Hi plus 1 by H naught, or you can write it as A, and for the composite walls also there was infinite number of resistances, so L by Ka and all. So here these things are not there, so A is anyway constant, so you can find out the overall heat transfer coefficient as like this. So Hi is given, H naught is given, find out the U, and then you can just replace it here. And here also you know everything, Th is the final, I mean the outside, that is 500. Then T is the final, that is 450. Ti is 300. Rho is given, maybe rho is given as 1200 kg per meter cube. Cp is given as 2200. Then volume is also given 2.25 meter cube. And then U you find out from here. T is also given that is 60 minutes is given here. So you just find take this in seconds, 3600 seconds, and then you don't know what is as here, right? As is not given anywhere. So you just find out everything else you know in this equation. You just need to find out how much is as. From as, what you'll find out, what is the question given here as what is the required length in meter of the submerged tubing. So L is given by, as is length into diameter. So L is given by as divided by D. D is given, right? How much? Yeah, D is given. This is D is equal to 0.02 meter. So just find out the length from here. Just calculate it.
So the question, man. Question.
Could you find out?
Declare the answer. There will be some
Yeah, yeah.
problems in
Here,
calculations.
here, I think I have done a mistake. This t, if you keep here, then it should be the opposite. dt by th minus t, the uas divided by rho vcp into dt. Yeah. So this should be the integration from t equal to t 0 to small t equal to t. So at t equal to 0, it is Ti, final temperature is T. This is the right one. Okay, just solve this and anyhow, you will get some expression from here. Then you calculate the U from here, from HI and H naught, that is the overall coefficient. And then rest all other values you know. You just need to find out the AS from there, and you can find out the L as given by AS divided by D. So the answer is 21.8 meter. So check this later, okay? You should be able to get the answer as 21.8. Okay, we'll go to the next question. A fin surface consists of root or base area of 1 meter square and fin surface area of 2 meter square. Okay, so suppose if this is the fin, so this is the base area, okay? Base area of the fin. Base area means which is connected to the this base wall. So this is given to be 1 meter square, and the fin surface area is given to be 2 meters square. The average heat transfer coefficient for the fin surface is 20 watt per meter square Kelvin. H is given. Effectiveness is also given. As E epsilon F is 0.75. If the fin surface with root or base temperature of 50 degrees Celsius is, that means this base wall, this is having temperature of 50 degrees Celsius, is transferring heat to fluid at 30 degrees Celsius. That means the surrounding fluid is at 30 degrees Celsius. Then what is the rate of heat transfer? Okay, so how do we proceed here? From this effectiveness, what do we get? Effectiveness is QF, Q with fin divided by Q without fin. Okay, so Q fin is given by what was the formula? Is PKAC into theta. So Q without fin, how much do you get? How much is Q without fin? Here we don't know what shape is it. I have just drawn it as rectangular shape, but we don't know what shape. The shape is not given here. They have just given the base area. So we don't know how to calculate this AC. So instead we know if base area is given, this base area is given, that is 1 meter square. So base area is included in Q without fin. That is HACB into theta B. Alright. So page Q fin Q without fin. So instead we can find out Q fin. So epsilon naught, sorry, epsilon F into Q without fin. Epsilon F is 0.75 into Q without fin is H W. So 0.75 into H is given, right? So how much was H? 20. And ACB is given as 1 into theta. Theta is TB minus T infinity. That is 20 degrees Celsius. Okay, you'll get some value here. This is Q fin. How much do you get here? 20 into 20, 475. 75 into 4, 300. So this is Q fin, okay? We have find out. But they have asked if fin surface with root or base temperature is this and transferring heat to fluid at this, then what is the rate of heat transfer? That means they're actually asking the heat without the fin. If they not mention anything, then you should consider it as heat without fin. Rate of heat transfer without fin. That means this one you need to find out. How much is it coming? 300 divided by 0.75. 400 watt. Anyways, you can directly find out from here also. Okay. Q without fin already you can directly find out. HACB into theta. You know H is given, AC is also given, theta is also given. Everything is given, so directly you can find out. There was no need to do all this. And just in the question, you need to understand which rate of heat transfer is asked to find out. If finned surface with root or base temperature is 50 degrees Celsius, that means the base wall is 50 degrees Celsius and transferring heat to fluid at 30 degrees Celsius, then the rate of heat transfer is here. So 400, 450, 500, 250. So the Q without fin they have asked to find out. So it is around 400 watt. You got this question? Okay. We can go to the next question, I think. So this is the last question of today's class. A long wire of diameter 1 millimeter is submerged in an oil bath of temperature T infinity. So this is an oil bath and a long wire of diameter 1 millimeter. So this is 1 millimeter is given. This is 25, T infinity is 25 degrees Celsius. The wire has an electrical resistance per unit length of Re. This is per unit length resistance. Okay, Re equal to 0.01 ohm per meter. If a current of I equal to 100 ampere flows through the wire, the convection coefficient is H equal to 500 watt per meter square Kelvin. H is given. Then what is the steady state temperature of the wire? Okay, so first of all, how do we proceed such? Again, this is a case of lumped system. For this, for to find out what is the steady state temperature, we need to equate. When does this steady state come? I mean, whenever there is the uh, heat transfer is, I mean, it is uniform. I mean, from the wire, the heat from the wire is this. I mean, the heat generated in the wire is the same, which is convected outside. Okay, so then only the steady state. If you balance those two heat, then only the steady state temperature will come into picture. So how much is the heat generated, or maybe you can say because of the electrical supply, current supply, there is heat generated in the wire. So how much is it? For current, heat is given as I square RT, right? So you can find it out per unit time also. I square R. Now what this is equal to, this heat is equal to, this is not Q actually, this is heat some energy. This is the heat energy divided by Q, this will become power, or this is only the heat. So this is balanced by the convection term. Convection, I mean, the how much heat that is being supplied to the wire, or how much heat, I mean, is generated in the wire, that is equal, that is balanced by the heat convected outside. So convected outside is H AS into T minus T infinity. We don't know what is the temperature of this wire. So this is the steady state temperature we need to find out. Okay, so how do you find this out? I square R divided by H AS is equal to T minus T infinity. So T is given by I square R divided by H AS plus T infinity. Okay. So find out what is the T, how much is T. I, you know, it is 100 ampere. R, you know, it is 0.01 ohm per meter. It's per unit length, okay? Then HAS, H is given as 500. AS is the, again it is this area, okay? So A is given by 2 pi RL or simply pi DL. So just calculate how much it is coming. And T infinity is 25 degrees Celsius. How much is it coming? Just let me know. Here you don't need this L. Why you don't need this L? Because anyways this R, the resistance which is given, that is divided by L, okay? That means per unit L. So anyways that L and this L will get cancelled out. So you don't require this L. This L and this L you cancel out. How much you get? This is 100 by 500. 3.14 into 0.001 plus 25 degrees Celsius. How much do you get? Have you got the concept up till this point?
48 degrees Celsius.
48 degrees Celsius.
Yes.
Okay, the answer is actually around 88.7 degrees Celsius. I don't know, I have not calculated this, but the answer is given to be around this. So you please check the calculations once again. This might be wrong also. This might be wrong also. I have not calculated it.
Okay.
You You check this again once more. Then we'll just continue with the concept part. Okay, you calculate it later on. From the time the current is applied, how long does it take for the wire to reach the temperature within 1 degree Celsius of the steady state value? So for this, you need to find out if it is, I mean, how to conclude whether it is lumped. Again, B Biot number, if you calculate HL by K, it should be lesser than 0.1. Then only you get it as lumped model. Okay. So from the time the current is applied, how long does it take? So for this, we go for energy balance. How do you get the calculation? Sorry, accumulation. Accumulation is the MCVDT term, CPDT term. Okay, that is the energy accumulated in the surrounding. So they have already given the rho MCP by T. So mass is given as rho VCP dt by dt. So output is the convection term. Generation is the current generated. I mean the heat generated due to the current. Then accumulation is this storage part, the storage energy storage part. So here you get H instead of AS you can write as pi dl, right? Pi dl Ts minus T infinity plus I square RL. Here I have multiplied with L because the R is given as per unit length. Then rho V is also given as AS into L. Cp dt by dl. Here you can just cancel out the L. Then you have to integrate this. Okay, but this integration is not that straightforward. You just need to check how the integration can be done because if you for this temperature you need to take this below here, but if you take this below then even in this term again the temperature term will come. Again this dt if you multiply here, then here also dt will come, here also dt will come. So for this type of equation you require the integrating factor. You need to integrate with that integrating factor method, so that if you remember the formula, it's given by YIF is equal to QX IF dx plus C. Okay, here Y is suppose capital T IF Q of small t IF dt plus C. And what is this IF? E to the power of p dt. So which part is p actually? You have to arrange this equation in such a form that it comes in the form dt by dt plus p t of p is equal to q t. So you have to arrange this equation in such a form, and then you can continue the integration. You must have done all these things, right? In already in class 12 maybe, or in first year. So if you arrange this, how will you get? Okay, I think the link is still 7:30. So just integrate this, then you get, you just find out how much is the time. Okay, the time taken. If you integrate this, you'll get some, all other values will be known, and you'll get the, you can find out this time. Yeah, so do this by yourself. If you don't get the answer, then you just let me know in the next class, or we can also solve in the next class. It's almost 7:30. So have you got this? Okay, so we'll continue in the next class. Thank you.